everyone. Welcome to the NPTEL MOOCs course titled Artificial Intelligence in Industrial Management Engineering. And I am Dr. Deepa Philip. I am a professor in the Industrial Management Engineering Department of IIT Kanpur. And this course is offered as part of the NPTEL MOOCs bucket from IIT Kanpur. And along with me, Professor Dr. Prabal Pratap Singh is also teaching this course. And we are in the week 4, where we have been looking into the topics of searching and why search is an important aspect of artificial intelligence, AI domain. And we have been looking at this point uninformed search, or what we call as blind search. And in the previous class, we looked into what we call as a breadth first search. So if you look into the slides, we saw what's a breadth first search, and we also saw the properties of the breadth first search. And now we are going to talk about what we call as another one, which is called as the depth first search, DFS. Okay. So in this case, you will say that the fringe, we know what is a fringe. It is a set of nodes that are, we already seen what it is. Fringe is a set of nodes generated, but they are not expanded. The fringe can be maintained as a last in first out. Okay. LIFO, last in first out queue. Okay. So LIFO queue, also known as stack. Okay. You can use a stack. Okay. It's a LIFO queue. Okay. Can be also implemented. You can also implement this, or it can also be implemented recursively. Okay. You can use recursion. Recursion is, what is recursion? If you remember, recursion, function calling itself. Okay. That is recursion. Okay. You can implement this recursively. So the logic is that DFS, you given a node, DFS is the function. If so, below this, if goal node return solution node. Okay. For each successor of node, okay, return DFS successor unless it is failure. Okay. Then last one is return failure. Okay. So you can implement, you can call the function in itself. Okay. You can call it the function by in itself. You can see that. Okay. You can recursively implement this. All right. But breadth first is not good for recursive implementation. Now, some of the properties of the depth first search, DFS, what are the main properties of it? Okay. So the first one is, we saw that BFS is complete. Okay. DFS is not complete. Okay. The reason is, it might cycle through non-goal states. It's a possibility of cycling through non-goal states. Okay. Then if solution found, okay, generally not optimal. Okay, / shallowest. The solution is not mostly non-optimal, it is also not the shallowest solution. Okay. Then if every node has B successors, okay, successors, which is the branching factor. Okay, the branching factor. and we must search to depth m, the fringe is at most Bm. Okay. So, the advantage of this is, so if every node has B successors and we must search to a depth of m, then the fringe is at most Bm, B multiplied by m. This means much better space requirement. Okay. It is not like breadth first where the space requirement is crazy. So, it is much better space requirement. Number 2, actually many cases do not even need to store all fringes, all of fringe. So, you do not need to store all of the fringe either in many cases, okay, because if you are implementing by recursion, then you do not need to store many things at all. Okay. Then time, okay, still need to look at every node. We need to still look at every node. Okay. And this is why this is inevitable for uninformed search methods. Because at each uninformed search methods, you because only can test whether it is goal or not. That is the reason. So, you have to go through every node. So, that is the major properties of depth first search. Now, can we think about combining the good properties of BFS and DFS, the breadth first search and depth first search. Okay. So, if we combine both, what will you get? Okay. The thing is called as limited depth DFS. Okay. Let us call it as limited depth DFS. We call it, it is like, what is it? It is just like DFS except never go deeper than some depth D. So, it is like a depth first search, but it will never go deeper than some specific depth D. So, then the other one is, let us now write the other one, second option, iterative deepening DFS. Okay. Iterative deepening DFS. What it does? So, let us write about it, or say this is called limited depth DFS with depth 0 if unsuccessful, call with depth 1. If unsuccessful, call with depth 2, etc. Okay. So, what you keep on doing is you first call limited depth DFS with the depth 0, then if it is unsuccessful, you call it with depth 1, unsuccessful, then call depth 2, etc. Okay. So, this is complete and finds shallowest solution. the space requirements. So, it is like BFS in space requirements or the computation space requirements of DFS. Unlike breadth first search, the space requirements is much smaller. Okay. Then key point that you should think about may seem wasteful. You may think about this as wasteful time wise because of replicating effort. Okay. You may seem that time wise this is wasteful because the effort is replicated. You are calling with each successive depth. Okay. It is really not wasteful, really not that wasteful I would say, okay, wasteful because almost all effort is at deepest level. Almost all of your effort is at the deepest level. Okay. And since you are limiting the depth and you always will end up finding the shallower solution. So, it is actually not that bad compared to the breadth first search. So, another thing is now let us talk about searching backwards from the goal. Okay. So, sometimes we can search backwards from the goal, Okay. You can search backwards from the goal. Okay. So, examples maze puzzles, okay. Then AIDS puzzles, reaching location F, okay, F being a final destination. Okay. Okay. Then question. This is a question for you. Okay. What about the goal of having visited all locations? Okay. Can we do that as is it an example of backward search is good? So, this question you need to think and answer. Okay. So, now you need to be able to compute predecessors. Earlier case we were computing successors, here you are computing predecessors instead of successors. Okay. The previous case we were taking that each move or we were looking into action was getting the successor. In this case you have to compute the predecessor. Okay. What is the point? Okay. Why this is important? Why is this important? Why is the compute predecessor is successor? Okay. Predecessor branching factor can be smaller than successor branching factor. Okay. Compared to the successor branching factor, predecessor branching factor can be smaller. So, the computationally it is much easier to do this. Okay. Fine. So, now that we have gone through many examples of what we call as the uninformed search or blind search, now let us talk about what is an informed search, okay, and discuss about some aspects of informed search. Okay. So far we assumed that no non-goal state looks better than another. The key thing is we assumed that no non-goal state looks better than the other. Okay. So, every non-goal states are the same. Okay. The key aspect of this is this assumption is unrealistic. You have to understand that this assumption is unrealistic. Okay. And why is it unrealistic? It is unrealistic because few reasons. Even without knowing the path, some locations seem closer to the goal than others. Okay. So, even without knowing the path, some locations may seem closer to the goal than others. That is number one. Okay. So, that is the main point. So, that is the logic. How can you capture? So, the idea here is it makes sense to expand closer seeming nodes first. So, the logic is that expand the closer seeming nodes, okay, closer seeming, the one that appears closer to you, and expand it first. Okay. So, the informed search strategies. What are some of the major informed search strategies? Okay. And how the first thing is use problem specific knowledge. Okay. First thing is you use problem specific knowledge. Okay. Then can find solutions more efficiently than search strategies that do not use domain specific knowledge. Do not use domain specific knowledge. Okay. So, the informed search strategies, you find some problem specific knowledge and you use it, and why? Because it will help you to find solutions more efficiently if you are not using any problem specific knowledge. All right. So, now let us talk about something called heuristics to begin with. Okay. So, the key notion here, okay, key notion. Okay. So, the heuristic function h of n gives an estimate of the distance from n to the goal. Okay. So, the heuristic function h n, okay, gives an estimate of the distance from n to the goal. So, this is the seemingly closer, okay, or the other word that we used here was closer seeming or seemingly closer to the goal. So, then other one is we have to think about is h of n is equal to 0 for goal nodes. If it is a goal, then the h of n, the heuristic function h of n is equal to 0. Okay. So, let us look at it as an example. Okay. Straight line distance straight line distance for traveling problem. Okay. Let us use a straight line distance, the problem domain specific knowledge. So, we have our network that we drew earlier, A, you have B, distance is 3, you have C, B to C, the distance is 2, C to A, the distance is 2, and this is the start node. Okay. Then you have D, distance is 3, and then E, the distance is 4, and there is F, the distance is 4, and here the distance is 9. Okay. And F was the goal state or goal node, okay, or node or state, you can call it as node or the state. Okay. Now, now let us say okay, we are saying that H of A is equal to 9, H of B is equal to 8, H of C is equal to 9, H of D is equal to 6, H of E is equal to 3, H of F is equal to 0. Okay. So, the H, the heuristic function for this is the straight line distance. Okay. So, these are the straight line distance. Okay. This is your problem specific knowledge that is given. This is in, so H A means A is like 9 units closer to the goal node, the straight line distance. B is like 8 units straight line distance. C is 9 units straight line distance, etc., etc. Okay. So, what we have done is we have added something new to the problem. Okay. We have added something new to the problem. Okay. So, then second thing, and what is this something new? The straight line distance. So, this is the domain specific knowledge or problem specific knowledge. Domain, yes, problem specific knowledge. Okay. Then we can use heuristics, heuristic, to decide which nodes to expand first. Okay. You can use the heuristic. Now, the heuristic, which is a straight line distance, you can use this heuristic to decide which nodes to expand first. Okay. So, let us work a small example, the greedy best first search. Okay. Let us look into this, how this one. Okay. So, the key point is expand nodes with lowest HN, the heuristic HN values first. Okay. So, whichever has the lowest heuristic, which is the HN here is the straight line distance. Okay. If you look into this, the HN is the straight line distance. So, anyway we have to start at A. Okay. So, let us start at the beginning, the state equal to A and cost is equal to 0, H heuristic H is equal to 9. Where do we get 9? It is said H of A is 9 given to you, right. Now, from there you have two branches. Okay. Oh, my bad, comma H is equal to 9. Now, let me draw the branches like this. Damn it. Okay. Two branches. The first is the, so if you can see the network, you can see that it can go to B or D. Okay. So, state equal to B, cost is equal to 3, H is equal to, what is H? H of B is 8. Okay. So, is 8. This is state equal to D, cost is equal to, cost is also 3 and H of D is 6. Okay. Cost equal to 3, H is equal to 6. So, given that now we have the problem specific knowledge and we know that this is seemingly closer. Okay. So, now what will we do? Because it is seemingly closer, we will expand this. So, from D where can you go? You can only go to E. Okay. So, state equal to E, cost is equal to 3 plus 4, that is 7, and H, which is H of E is 3. So, this is the H we are talking about. Okay. H is equal to 3. So, now we can see that this among these two nodes B and E, it is still seemingly closer, okay, compared to the other one. So, from E where can you go? You can go only to F. So, we go to state is equal to F, cost is equal to 7 plus 4, which is 11, that is a 4, this we are talking about, okay, 11, and H is equal to 0, means this is the goal state. Okay. So, you can see that it main thing, it rapidly finds the optimal solution. Okay. It rapidly finds the optimal solution which is the state F, and the question is, does it always? In this case it found the optimal solution, but does it always find this optimal solution? This is a very good test case for us because of and so if you look into this, what we have done is the straight line distance which is a problem specific, which is a domain specific knowledge added to the problem helped to decide which state or node to expand. Okay. So, once we add the domain specific knowledge, it helped us to decide which node or state to expand. Okay. This domain specific knowledge, this is what we call as the information, the additional information that we ended up adding to this problem. Okay. Now, the greedy search, even though it appears to be an optimal, rapidly finds the optimal solution, the critical question is, will it always find the optimal solution? We will talk about this in the next coming class. So, thank you for your patient hearing, and I will see you soon with the next lecture of this week. Thank you very much.